All right, let's continue our discussion on convection. So as I was saying before, convection is driven by buoyant forces. And so when we're looking at convection, the hot material will rise because it is less dense, and the cool material will sink because it is more dense. Okay, so let's go ahead and look at an example. This is 14.7. It states that most houses are not airtight. Air goes in and out around doors and windows, through cracks and crevices, following wiring to switches and outlets, and so on. Okay, the air is in a typical house is completely replaced in less than an hour. Suppose that a moderately sized house has inside dimensions of 12 meters by 18 by 3 meters high. Okay, and that all air is replaced in 30 minutes. Calculate the heat transfer per unit time in watts needed to warm the incoming cold air by 10 degrees Celsius, thus replacing the heat transferred by convection alone. Given the specific heat of air is 1,000 joules per kilogram degree C, and the density of air is 1.29 kilograms per meters cubed. Okay, so again, we're looking for Q over T. So first, let me go ahead and keep this time, or I'm sorry, take this time and convert it into seconds. So there's 60 seconds in a minute. So our time is 1800 seconds. Okay. We can also calculate our volume with these dimensions here. Okay, so if we multiply this out, so V is going to be 12 times 18 times 3 meters cubed. Okay, we can go ahead and multiply that out. Let me see real quick. 12 times 18 times 3. That's going to be 648 meters cubed. Okay. All right, so we have all of our knowns. We are looking at the heat transfer when delta T is 10 degrees Celsius. Okay, so the first question is, what is our mass of this amount of air? Okay, so remember before I stated that density is a mass over volume. So we can find our mass of the air by saying this equals to density times volume. So our density of the air was given as 1.29 kilogram per meters cubed. My volume I just solved for is 648 meters cubed. So that will be 836 kilograms. Whoops, sorry about that. Kilograms. So that's my mass of the air in the house. Okay. Now what we need to do is find our heat transfer from that change in temperature. So Q is going to be MC delta T. Okay, so our mass of the air is 836 kilograms. C, so for air, is 1,000 joules per kilogram degrees Celsius, and our delta T is 10 degrees Celsius. Okay, so our heat transfer due to the change in temperature of the house, the air in the house, is 8.36 times 10 to the 6th, and this is in joules. Okay, now our third step is to find our Q over T. Okay, so what is this heat transfer per unit time? And it does ask for it in watts. Remember that, I'll just write it real quick over here. watts is in joules per second. Okay, so that's why I also translated this into seconds. All right, so we'll take our Q, which we just solved for, 8.36 times 10 to the 6 joules. We'll take our time in seconds, 1800 seconds, and we get 4.64 times 10 to the third watts. We could also put this in kilowatts, so that would be 4.64 kilowatts. Okay? These are both correct. All right. So that's the rate at which the heat transfer is occurring. Okay? All right, let's move on to one more example. Example 14.8, it states the average person produces heat at the rate of about 120 watts when at rest. At what rate must water evaporate from the body to get rid of all of this energy? Okay, and so this is that one where I mentioned that you might want to know the, I think it was the latent heat of vaporization of water in the body. Yeah, so we want to make sure that we understand how to find that. So let me go back to, oops, sorry about that. Here, so let's go back to latent heat. Is this it? Yes. So for water, the latent heat of vaporization, I'm going to click this button down here, and it's going to tell me for water in the body or at body temperature, it's going to be this 2,430 kilojoules per kilogram. Okay, so let me go back here. So we will need to use this. So again, we know that Q over T is equal to 120 watts or joules per second. Okay, and we want to know M per T, so the mass per time. Okay, so we know that Q over T is equal to M, we can write it as, MLV over T. Okay, since Q for a phase change is MLV for vaporization. Okay, so that Q equal ML sub V. Okay, and so we can rearrange this to being M per T, and that'll equal Q over T over 1 over V. Okay, and so we can simply plug that in. So 120 joules per second is going to be times 1 over LV, and that's what we were just looking at. That was 2,430 kilojoules per kilogram. Okay, so because this has a kilo aspect, this has a kilo aspect, we know that 1 kilojoule is 1,000 joules, 1 kilogram is 1,000 grams. If we were to plug those values in to convert them into grams and to joules, it would be the same as just going, okay, the kilo and the kilo cancel. Okay, you can write it out, it might help you, but for the sake of this, I'm just going to say these will cancel. Okay, so this will give me a value, let's see, 120 over 2,430 of 4.94 times 10 to the negative 2, and this is in grams per second. Let me go ahead and translate this into minutes. So I'm going to say 60 seconds per minute, and I get 2.96 grams per minute. Okay, so this is the rate at which water must evaporate from the body to get rid of that energy. Okay. All right, so the last one is called radiation. Okay. And what's interesting about radiation, the first thing is that there is no medium required for this to occur. Okay, radiation happens in space. Okay, that's how we can detect stars and so forth. Okay, the energy of electromagnetic radiation depends on the wavelength and varies over a wide range. Okay, a smaller wavelength corresponds to a higher energy. Okay. More heat is radiated at higher temperatures. All objects absorb and emit electromagnetic radiation, whether it be a very small amount or a higher amount. Okay, we do too. The rate of heat transfer by radiation is largely determined by the color of the object. Okay, black is going to be the most effective color, and white is going to be the least effective color. Okay, so let's go ahead and look at this here. So this is a plot of intensity versus the wavelength, okay? And this little section right here is going to be our visible range, or our visible light range. This is what we can see with our eyes. And that's going to be colors violet through red. So violet has the shortest wavelength in the visible range, while red has a higher, wavelength. And these are curves showing the temperatures at which these are occurring. Okay, so you can see that all of the hotter stuff, right, this 6,000 Kelvin, so this is hot, the hottest here, that will have the most intensity where we are at a lower wavelength. Okay, so smaller wavelength, higher intensity, higher temperature. Okay, if we have a lower wavelength, we have lower intensity and a lower temperature. I'm sorry. Okay, hold on. Let me write this out. So short wavelength, that is a lambda. We have high intensity and high temperature. Okay. If we have a longer, I should say long. If we have a long wavelength, we have lower intensity and a lower temperature. Okay, so keep those in mind. That's how you're reading this here. Okay, now we can look at these two here, just kind of looking at the different flames and the color between. Okay, so as you can see, this blue or white color is going to be the hottest versus the flame out here has cooled down a bit, and so that's cooler. Okay, so touching at this part of the flame versus this part of the flame, it's gonna be different in temperature. Okay, when we're talking about the effective, least and most effective, okay, we can think of this as a way to, I guess an example would be, like this is saying, looking at blacktop versus cement. So cement is more of a gray color, blacktop is black. And when you have ice on both of these surfaces, the ones with the black is going to melt much faster, okay, because it is the most effective. Okay.